Today is fifth session. Welcome all young participants and curious colleagues. Thanks Professor Arvind Kulkarni, though he is not here today in the meeting. IIPT President Professor Aluwalia and organizers RC22 for giving an excellent opportunity to team up with esteemed team members, including course coordinator Professor Vandana, Dr. Rajiv, Dr. Jyoti, and Dr. Kiran. A special thanks to Professor Balakrishnan sir for his blessings. Sincere appreciation to all the participants for their curiosity they have shown and the sincerity for the lectures. Today, let us embark on a journey into the captivating universe of quantum cryptography. Is not a new concept. All great civilizations have developed techniques to send communications in a secured way. These civilizations also made use of secret keys. Cryptography is one of the oldest sciences and it ensures that two parties communicate safely without any interruption or without being your communication leaked. Cryptography is all about encrypting and protecting data so that only the person with the correct secret key rather, can decrypt it. It ensures confidentiality and this is done to protect sensitive information being leaked. A typical example is the messaging tool WhatsApp, which encrypts conversations between people to ensure that their messages should not get hacked or intercepted. Cryptography, it differs from traditional cryptography system. And nowadays it is called as classical, the traditional cryptography is called as a classical cryptography. These differences in an attractive way, and I failed to resist my temptation to put it on the slide. Classical cryptography is widely used, well established and tested, and it is easy to use. Whereas quantum cryptography is sophisticated and still is in early stage of deployment. Classical cryptography can span millions of miles, whereas quantum cryptography has a very limited range, the most successful of which was able to distribute the key across a distance of 833.8 kilometers. 1968, Stephen Wessner, very few know about him, from Columbia University in New York. He was the first to propose the concept. His seminal paper titled Conjugate Coding was rejected by IEEE Information Theory Society, but eventually published in 1983 in SIGAT News. A few notable researchers, quantum physicists, they developed the concept of, later on, they developed the concept of quantum cryptography. One of the key pioneers is Charles Bennett, who along with Gilles Brazet introduced the concept of quantum key distribution in their groundbreaking paper titled Quantum Cryptography, Public Key Distribution and Coin Tossing in 1984. The principles of quantum mechanics which have contributed to give us the system which can keep our information secured for lifetime. A quantum property cannot be observed without change. Heisenberg's uncertainty principle gave us this property, and no cloning system said that whole particles cannot be copied. So with these properties and after getting into the idea that the photons can transmit information, building upon this work, Bennett and Brazet in 1984 proposed a method which is named like BB84 for secure communication. BB84 protocol, it uses photons to transmit data over fiber optic wire. So what is photon? A single photon, actually what is single photon? So a single photon represents a very tiny amount of light. These light waves are electromagnetic waves and they can vibrate in different directions as they propagate through space. Now, how a single photon is generated? So drive a single atom, by the laser and excite that. Switch off the laser, and now the single atom, after some fraction of second, depending on the atomic lifetime, will emit a single photon. And nowadays, a quantum dot is on demand single photon source. Now let us learn about what is polarization. But before jumping to that, I would like to make it very clear to you that why I am taking all these, why I am telling what is photon, what is single photon, how it is generated, what is polarization and all that. Because after this, when we will be learning quantum cryptography model, so that time all these terminologies will help you to understand that model. So prior to that, if you have the clear idea about these and something will not run in back of your mind just to think about what is photon, then how will it be generated, and then what is photon polarization and what all ma'am is talking about. So for that purpose, I am taking this. The direction in which electric field of light wave vibrates, that is called as polarization. Photons can be oriented or polarized in a specific direction, and thus qubits can be implemented using polarization of a photon. Now, each photon, it can represent a qubit. Qubit means quantum bit. You have heard a lot about it, and now you are very well acquainted with qubit. So qubit is nothing but it will also hold a bit. So actually our machine understands only the language of 0 and 1, nothing else. So when we talk about the classical bits, they are 0 and 1. And when we talk about the qubits, they are also 0 and 1. Only the difference is that the qubit can hold 0, it can hold 1, and sometimes it can also hold both at the same time, 0 and 1. Here that our quantum bit, it must have two distinct states. Why? Because we need two distinct states for representing zeros and one. So one should, whenever any basis you are taking, in that basis you should have two distinct state, and out of these two, one should represent 0 and another should represent 1. Because I have already informed you that computer doesn't understand anything apart from the language of 0 and 1. Now the polarization state of a single photon makes it possible. How? Because the photons can be polarized in a particular direction. For example, and then we can assign values to those states. So as a terminology or as a standardized thing like horizontal and anti-diagonal. These polarized states are ascribed a logical value 0, whereas vertical and the diagonal polarized states are represented by logical value 1. So this way a classical bit 0 or 1 is encoded into the polarization of a photon, and this, how we will achieve this? Yeah, I was telling you that polarization means it is vibrating in all possible directions. So how will we make our photon to be on a one particular state? And that is possible. That is achieved with the help of filters. Polarization filter, which is also known as polarizer, it is an optical device that selectively allows the transmission of light waves with a specific polarization state while blocking all other light waves with different orientation. So on the screen, you can see the polarizer, right? And in this polarizer, there are two bases, horizontal, vertical, and another is diagonal. Now again, horizontal and vertical bases, they have two filters, which are the horizontal one and the vertical one. And you can see there that the horizontal one is being assigned a value 0. So physicists will say that our photon is in horizontally polarized, and computer scientists will say that it is 0. And again, when we'll talk about the vertical polarized photon, you will say it is vertically polarized. A computer scientist will say it is 1. So this is how we are able to achieve making our photon by polarizing it to give us the value as zeros and 1. Similarly with diagonal, in diagonal basis, plus 45 and minus 45, they call it as diagonal and anti-diagonal. If it is diagonal, then assigned value, logic value 1, and if it is anti-diagonal, then it is 0. Same is depicted below with the angular, 45 and all that. So the BB84 protocol model uses 4 polarization states. So if something is going in your mind that why only 2 bases, HV and diagonal, it is BB84 protocol model. It has used 4 polarization states. So we are binded with these: vertical, horizontal, 45 degrees right, 45 degrees left. Now, horizontal and vertical orientations are linear polarization states, and so are diagonal states. So all of them are linear polarization. In 1992, 6 years after this model, Charles Bennett, out of the two, one was Charles Bennett, I hope you remember, he presented a new quantum key distribution protocol and named by his surname and the year that was published. So the protocol is essentially a variant of BB84 protocol, with the main difference being that B92 uses 2 states of polarization instead of 4 that are being used in BB84 protocol. And along with its architecture, that an eavesdropper can be detected. So that care is being taken in that also. This is clear to everyone that these photons are polarized with respective polarizers or respective filters. Now, polarized photons, they are transmitted to receiver. They are transmitted to receiver. The sender has sent photons, polarized photons, and they are being transmitted to receiver over fiber optic cables, one by one. At the receiving end, there are 2 beam splitters. A beam splitter creates a quantum superposition. And you know it very well. Day before yesterday in that session, how to create a quantum superposition using a beam splitter, you have seen. You have been given knowledge about it. So now you don't have any difficulty in understanding this, that a beam splitter does create quantum superposition. Now then there is a photon detector which will measure or which will detect its for mapping their state. Now mapping is with which it will map definitely bit value 0 or 1. So whichever the photon with whichever state it will reach to will go to the detector. No one knows in superposition. No one knows that they have repeatedly you have been being made aware of that in superposition state, whether it will be had or tail, no one knows. So same thing will happen here in superposition. At the receiving end, the receiver doesn't know whether he is going to receive 0 or 1, whatever will be at that particular moment of time, so that will be detected by the detector. And before collapsing, photon is in superposition state, and therefore the result is uncertain till it collapses. With all this knowledge, now we are going to demystify that how the quantum cryptography model works, and that too BB84. Now, this model was proposed in 1984 by Bennett and Brazzard, and that's why the name. The idea was to encode every bit of secret key, because what is a secret key? It is nothing but it is a sequence of zeros and one. Now, all this, the idea was that every bit they should be able to encode into the polarization state of a single photon. The protocol then runs as follows. Now they have taken BB84 protocol itself, their model itself has taken, perhaps for making it more interesting, they could have taken it as sender and receiver, but instead of that, they've taken two virtual persons, Alice and Bob. And here Alice is the sender and Bob is the receiver. So whenever I call Alice, and then the Alice is nothing but sender. And whenever I use the name Bob, that means Bob is receiver. Now, Alice sends a sequence of pulses, each of which ideally contain single photon polarized differently. Alice encodes zeros in horizontal polarized photon. Now, it is up to Alice that what bit sequence she has to take, and just 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0. Who decided this? Alice. She wants to send this as a secret key. This bit sequence as a secret key. Now, what happens? Alice has encoded zeros into horizontal photons, right? Horizontal is always 0 and vertical means it is 1. So horizontal polarized photons, that is 3, she has given polarized, H polarized, and then she has encoded 4 into V polarized photons. So you can see there is a balance. But there are 14 photons have been sent. So what happens? Only half of the cases. This is only half of the cases, and the other half of the bits then randomly are again encoded using a diagonal polarization. Now, diagonal polarization basis is again in that diagonally polarized 4 and she has anti-diagonally polarized 3. So generally it is balanced. So this is the last one, and now this is the first one. So they are traveling and they are reaching to Bob. Just show them Bob, yeah. So Bob is there. Now, Bob, the receiver Bob, it uses beam splitters of his choice randomly using a standard setup, but he is free to choose any splitter. So there are two beam splitters. One is diagonal beam splitter and another one is horizontal vertical, which in short is called as HV. Bob has freedom to choose because he doesn't know which bases were used by the Alice. Which bases Alice has used, Bob doesn't know. So what Bob will do, according to his choice, randomly, he will fix, and then he will decide that this particular photon is to be received by diagonal beam splitter or HV. So it is up to his choice, and then they will be received by the photon detectors. Now, the detectors are used that to distinguish between H and V and the diagonal and anti-diagonal state, because detector will whichever state will reach to the detector, then detector will give the measurement will be either 0 or 1. So HV will take vertical as 1 and horizontal as 0, and our diagonal beam splitter will take diagonal as 1 and anti-diagonal with 0. So this is how the values will be measured. Once photons are detected and the measurement is done, they get destroyed. So Bob then publicly announces that which basis he used for each bit. Then Alice then confirms that in which cases they use the same basis. And they throw out all the bits which they have used with different bases and leave only those where they use the same one. After this procedure, the length of the key, the shifting key, which Alice has sent, will get reduced, and but it remains whatever will remain, which will coincide for Alice and Alice and Bob both. And then they check if there was any eavesdropping, and if any doubt, then the whole key is thrown and the procedure is repeated. Below gives an example of transmitting 14 bits of secret key, and after the key shifting only, you can count 9 bits are left. Now, I will just summarize this. I mean, the key points only, the very key points which we should understand completely at this particular level, that the intrinsic randomness of the quantum states and their measurement provides the randomness in creation of the key. And moreover, QKD exploits no cloning theorem, where quantum states cannot be cloned, they cannot be copied. So we have a unique key. And furthermore, the uncertainty principle that is presented by German physicist Heisenberg make the quantum key distribution process strong against any interception or retransmission attempt by the eavesdropper. How, that we will see later. So please go to, let us solve this, that how they have got the shifted key. In this case, actually, it is the same picture, but let us try to see what is the shifted key in this case. Now we know this is the bit sequence, you know the Alice bit sequence, which is 1 0 1 1 0 0 1 1 0 0 1 1 1 0. Now for because the school students are also there, for young participants actually, I have made this table out of this only. So in this table, the polarizers are now polarizers are represented like this. If it is HV polarizer and the depolarizer. Let us write Alice bit sequence first. So please come to Alice bit sequence. Yeah, same I have copied. Okay. Now from where I got these states. So states I have copied. How I have copied? So you can see double arrow. Now they have used the concept of double arrow. So double arrow means vertical is shown as vertical. That means 1. Well, will carry value 1. Horizontal is horizontally clear cut. They have showed that this is in horizontal position. And then for diagonal, it is like this. Okay. As you can see in this, from this diagram only I have taken. Bob has applied HV. After that, diagonal, then HV, diagonal, HV, diagonal, HV, diagonal, HV. Okay. So I have just copied it. Observe that you can clearly see it. Now Bob has applied this and he doesn't know what will be the measurement because photons are in superposition. So what will reach to the detector is unknown to Bob, and he has got this measurement 1 0 0 1 0 0 1 1 0 0 0 1 0 0. So this is assumption. This is purely assumption. We have assumed that Bob's detection was like this, and what after measurement Bob got this. Now they both Alice and Bob, they will tally their sequences. Now while tallying, now see what happens. How shifted key is made. Shifted key will be made in first case. It is HV vertical, and at the detection time also it is HV basis and it is vertical 1. So it tallies totally and therefore 1 will come there. In second case, can you please explain in second case?
I mean, Alice case, it is HV horizontal, but in Bob's case it is diagonal.
Diagonal, so it will be discarded.
Discard.
Discarded. Shifted key will be dashed there. Okay. So this way it will go on, and then at last we okay. Wait, let us take one more example. Third one. In that case, the polarizer is D plus 45, and Bob's detection, he has applied which beam splitter? HV. So plus is HV and cross is diagonal. So Bob's measurement will be 0. So this is what Bob has got. Okay. So because the bases themselves are not telling, so definitely they will be discarded. Now one case where it has been accepted, take to any other case. Second cell, the bit value is matching where? Yes, the bit value is matching, but the bases are different. This is HV and this is diagonal. So if basis is different, they are discarded. The bases are different. If the Alice has used HV and Bob has applied diagonal splitter for them. So they are mismatching, and therefore, although they have same value, eigenvalue is same 0, 0, but they will be discarded because here they mismatch. So in totality, they should match. In the first case, you can see that the HV polarization is there, and then here it is plus. That means here also HV. So therefore, they are aligning and compatibility is there, and therefore it will become one of the part of secret key. So this way, we have seen that the shifted key is 1 1 0 0 1 0 0 1 0. So let us try one. What will be the compatibility in first case?
As the bases are not matching, it will be dash.
As the cases are not matching, it will be dash. Yes. Second case?
Both are matching, so it will be
Both
1.
are matching, it will be 1. So please write.
In the third case, the bases are not matching, so it will be dash.
Yes.
In the fourth case, both are matching, so it will be 0 here.
0, yes.
In here, also both are matching, so it will be 0.
0.
In here, also both are matching, so it will be 1. In here, the bases are not matching as well as the values are not matching, so it will be dash.
Discarded, yes.
In here, the bases are not matching, so it will be discarded. In here, both of them are matching, the state and the bases, so it will be 1. In here, the bases are not same, so it will be dash. In here, both are same, so it will be 1. And here also both are same, so it will be 0. So the shifted key
key will be 1 0 0 1 1 1 0. So did you get the same?
Yes, ma'am.
Let's move ahead.